Okay, so we're going to continue the modeling of signal generators using the cylindrical rotor machine as one example. So for cylindrical rotor generator, we have 6 windings to model, 3 on the rotor and 3 on the stator. And on the stator side, all the windings are connected at the same point into the ground, which is a neutral point. And the other 3 terminals will be sending electricity to the network. And on the rotor side, the 3 windings are isolated from each other, so they don't have physical connection, but all the 6 windings are coupled by the same electromagnetic field. To list the equation, so we can have one voltage equation based on the Kirchhoff voltage law for each winding. So on the rotor side, we have the instantaneous voltage as source. So even actually only source is actually the field voltage, and the other 2 voltages are basically 0 under normal conditions. So they're only non-zero under some conditions when the rotor is shaking or oscillating. So we have voltage, instantaneous voltage on the left-hand side, and right-hand side will be voltage drop on the resistance, and also voltage drop on the inductance. On the stator side, so the source will be really the voltage induced due to the change of the magnetic field in the winding. So we have the induced voltage, which is the first order derivative of the flux, and the right-hand side will be the voltage drop on the winding and also the voltage sent to the system. So if we put all the equations in the same, so we'll have same matrix form. So we have 6 equations, 6 voltage equations. And so you see for the resistance, that's basically a diagonal matrix. So we only have just resistance on each winding. And the current here may have a negative sign or positive sign depending on the direction. So for the stator windings, you will see a negative sign with the current. On the rotor winding, we don't have negative sign, so basically they're positive. Okay, so we can write into this matrix form. We have 2 vectors for voltages for the stator and the rotor, respectively. And then we'll have 6 flux equation. So talking about how the flux linkage of each winding change with the current, because all the windings are coupled together due to the revolving of the rotor. So there will have 6 by 6, 36 elements. Each represent either self-inductance if they're on the element, the diagonal element, or mutual inductances if they're on off diagonal elements. Okay, so later we use this analogy because for each to identify any inductance in the matrix which involve 2 windings. So for instance, if we use LAB as one example, so that will involve one winding A and the other winding B. And this magnet actually represents the rotor revolving between the 2 windings. So if we find this LAB, so both A and B actually with stator are stationary, so they don't revolve with the rotor. So only rotor revolve between A and B. So the inductance will reach the maximum value twice every each cycle, because that will have the minimal air gap. So when the air gap becomes minimal, so inductance will become the maximal. So when it turns by 180 degrees, so that will reach another maximum value. So we can imagine for any element here in this green box, because 2 windings are either different, like one from A, one from B, or both from A, both from the same winding. So their values will change with period of 180 degree. So after every 180 degree, so their value will reach the maximum. For everything in this gray box, so you see one subscript is lowercase a, b, or c, so that's stator winding. The other one is F, capital D, or capital Q, so they are from a rotor winding. So which is we can consider another analogy, which is those two stay together, so which could be rotor. Okay, this is a stator. For that case, so the coupling between the two windings will really depend on whether their axes are in parallel or orthogonal. So if the two axes are exactly in parallel, so that inductance will reach the maximum value. So it becomes orthogonal, so that that will be 0. And if it become opposite to each other, like one is facing the left and the other become facing the right, so their inductance will become negative, maximum value, but in the opposite direction. So which means for any inductance in those two gray blocks, they will have a period of 360 degrees. So if we use sine or cosine function to model how those inductance should change, so you're going to see either sine or cosine function, just sine theta, cosine theta. But for this green one, you will see cosine 2 theta or sine 2 theta plus certain phase. And finally, for this orange block, that's very simple because both winding capital letters, so which means they are from rotors. So the magnet and the two winding together, they revolve together. So everything here will be constant. So finally, we have, and this slide just show there for each individual inductance how they are going to change at the sinusoid. And finally, to summarize, for the inductance matrix, everything for the stator self or mutual inductances, they are all sine or cosine function of a second harmonic. So we'll see two theta in each function. The phase really depends on which one will be treated as the initial phase, 0 phase. So here we use axis A winding as the reference. So that's why for only the self inductance of winding A, you don't have any phase, but the other will have some phase change. For LSR, which is the mutual inductances between stator and the rotor, which means every inductance in this element will couple one winding from stator and one winding from rotor. So they, as we discussed, so they all are first order harmonic. So you see, if we use cosine function, so you will see only theta without 2. And finally, this element is very simple. Okay, all constant. So why do we have some zeros on some element? Because those zeros indicate the coupling between the damper winding in D axis and damper winding in Q axis. And when the two winding, one in D, one in Q, they all are orthogonal to each other. So there's 0 coupling. So that's why it becomes 0. All right, so now we have our first model. Go back to this slide. So we developed the first circuit model or equation model for the signal generator. The model is not good because it doesn't meet our expectation because we want to find a model with all constant parameter. We don't want to see any parameter which is changing with time. Just like if your operator, you do some operation on the transmission line or transformer, in the system, they give you the model. They tell you the resistance will change periodically. So that's definitely not convenient to operate, right? You need to have a different model, and even the model may be more complex, but all the parameters are constant, such as you can do the calculation based on the constant parameter, and you can even like test the model, validate the model, and do some simulation. But those models, depending on theta, definitely are not very convenient for engineer or operator. Okay, so let's do some quick analysis to see how can we simplify the model. Our goal is to get rid of the theta in those matrices. Okay, so if we want to introduce any transformation, we want to have still the flux linkage equation in similar form, but there's everything is theta independent. So in this model, only the LRR is theta independent, which means it doesn't involve any theta, right? Because why that case? Because it is in the reference frame rotating together with rotor. So both the LSS and LSR are using the reference with stator, because rotor is revolving relative to the stator. That caused some change, either the air gap or the coupling of the two windings. But for this last one, it is based on the rotor reference. So that makes it simple. So this gives us some idea. Maybe we can introduce some transformation revolving together with the rotor, and then we can generate some the new inductances doesn't depend on theta at all. Okay, so we pick the last equation from here. We pick this equation, the psi f dq, which is actually a vector of flux linkages of three elements, psi f, psi d, psi q, which is equal to the element in this block and multiplied by this column, right? So we'll have this equation. So in this equation, I highlight this component because this component is theta dependent. So this matrix has theta, but this one doesn't have theta explicitly. It basically just three elements of flux linkages. And this one doesn't explicitly include any theta because it basically just a vector of IA, IB, IC. And this one is a constant, right? That's completely constant. And similarly, this one doesn't consider any theta. This one is actually basically just direct current. So which means if we move this item, the product of this theta dependent inductance block and with the current vector, so right hand side, I color it in blue, it doesn't depend on theta at all. So which means we can make some change here, and so to create a new frame, reference frame in which the inductance matrix and current are both theta independent. Okay, so we can make a left-hand side of equation be theta independent. So what I mean is we can introduce some transformation. The transformation itself is theta dependent. It's a function of theta. Current, instantaneous current also may change with theta, and by transforming the current of the stator winding, so that can cancel the theta dependency. And also the invert, because when we add the transformation, we also need to insert the inverse of the transformation. So the invert transformation applied to the LRS also can cancel the theta dependency. So far we don't know what this transformation is, but we're pretty sure there must be such transformation because the right-hand side already indicate the theta dependency can be removed. Okay, we just need to figure out what that transformation P is. It is the path transformation we're going to talk about in a few minutes. Okay, so which means after transformation, we can have a new current vector in a new frame, which doesn't depend on theta. And then the new inductance matrix also all constant. So we just plug in this one. This is the LSR, which is this matrix multiplied by the current. So which is actually equal to this one. So we can, one idea is to find this new current, transform current. One idea is maybe we can let this row multiply by this column and to define a new current. We maybe I1. This is a new current. This is, we just call it new current. The current itself is just maybe state dependent or not dependent, we don't know. But good thing is we replace this whole bunch multiplied by this one by the first current. And so you see this row is same as the first row. So this one also generate the same current. And the third row is different. Multiplied by the column will generate another current. It could be, we can call it I2. Okay. So we didn't change anything, but we just make by defining the new current element I1, I2, we make a formula simpler. And we make this part doesn't depend on theta explicitly. It may become implicitly dependent, but that just make our formula simpler. But one problem of this definition is originally we have three currents. We have IA, IB, IC. They're actually both independent in any condition. So only in normal condition, we know the IA, IB, IC, they have the same magnitude, but 120-degree displacement. But for fault condition, the IA, IB, IC may not depend on each other. So we still need to introduce another current element for the three dimensions, right? So we can create another element, I3. We just simply define I3 to be their average, the average of IA, IB, C. So basically just the current going to the ground. All right, so next, let's just give you the path transformation, or we call it a zero DQ transformation. A zero DQ transformation is just change the current originally in the A, B, C frame into a new frame, zero DQ. So zero means the neutral element, which means the average or the total of the three-phase current. D means a current in the phase of D axis, and Q means a element in the Q axis. This is the path transformation. Okay, so you see the second row and the third row is exactly what we just discussed from previous slides. And the first row, basically, we put some constant value. So those multiplied by this row will give you the sum, the weighted sum of the three current of the stator. So this transformation, we assume three constants like K0, KD, KQ. They can take arbitrary value as long as they're not zero. For any non-zero value, they will be able to get rid of the theta dependency, which means if you apply this transformation to create the three new fictitious current, and so using the three new currents, the inductance matrix has no theta at all. But here we still want to make those K's, K0, KD, KQ, be somehow meaningful, right? So then next we can determine their some value, we can preferable value for those three K's. So let's just take a look at the steady state condition. So for steady state condition, when we say steady state condition, so there's a quiz question I asked. So under steady state condition, is every variable unchanged or constant? But actually they're changing all the time. It just to operator, they are not important, the change. So we can ignore their change. But here, that's why, so in our model for steady state condition, we can assume all the current, instantaneous current, they have the frequency exactly same as the stimulus frequency. And for the rotor, if rotor is revolving at a frequency or angular frequency omega r, that's same as singular frequency. So singular frequency is 60 hertz. Angular frequency is 60 multiplied by 2 pi, which is 377 radian per second. So for static condition, so all the current will be exactly accurate sinusoid at synchronous frequency and the same amplitude or same RMS value. So if this is case, we just plug in those value here in this column to see what we can generate for the transform current. So if you plug in here, so you will notice, so this omega s is with instantaneous current. And this theta is actually the actual physical position of the rotor. But if you assume the rotor is revolving also at a synchronous frequency, so you at the end the omega is cancelled. So ID become constant value. ID doesn't depend on time at all. The first element, this one. So it's completely constant because KD is constant, IM is the amplitude, delta is the angle. So under static condition, delta means how the QS is relative to some reference. Okay, so if you think about a lot of generators, they revolve together, exactly synchronized. And you can define any generator or their center of reference as the reference for delta. Then all the delta will be constant. So this is constant. And there will be a factor of 3.5. That's also constant. And this is completely constant. Also, the IQ is constant. Definitely for the balanced condition, I0 has to be 0. There's no current going to the ground. So original 3 instantaneous current, which are all sinusoid, changing with time, now become 3 elements, including 1 0, and the other constant. Okay, so this transformation does the job and to get rid of the theta dependency. They're all constant. So we can generate constant current. So by introducing this transformation, so even this itself look complex, but if we apply this one to the 3-phase current or later 3-phase voltage and also 3-phase phase linkages, will create current, voltage, or flux vectors all constant. So that's very convenient. So next, we still need to figure out what value we need to take for those 3 Ks, right? K0, KD, KQ. As I said, you can choose any value. It doesn't change the facts that they're all constant, but you still want the value meaningful. You don't want K maybe 10,000, right? You create some current which is like a 10,000 times of the actual current. That's not good. So let's see how we can find the more reasonable K values. So one condition we can add is we want the transformation to be power invariant. So what does that mean? A power invariant means if we use the instantaneous current IABC, which are actual stator current, to calculate any power, or we use those fictitious current, transform current to calculate power, the 2 power have to be equal. You don't want to calculate power in the original frame ABC, which gave you the generator is generating 100 megawatt. And when you transform everything to the 0DQ, it generates 10,000 megawatt. You want the 2 power to be exactly same. Okay, so let's figure out what how much room we have to determine those K value. Mathematically speaking, the power invariant transformation means the inner product has to be preserved. The inner product is basically just the power, right? You have voltage and current. The inner product of voltage power current will give you power. So which means power preserved or inner product preserved. So the 3-phase power is defined to be basically the power, instantaneous power of each phase. You add them together, right? In the course 421, we actually proved for a steady state condition, the 3-phase power, which is actually sum of 3 instantaneous power of 3 windings, is equal to 3-phase real power, because reactive power is actually from different windings, they cancel each other. All right, so this is the 3-phase power. So that's why we also use capital P, because that's also the three-phase active power. So this one is defined to be the sum of the three product, which is actually the inner product of the vector voltage and the vector current. So because each vector here is a column vector, so to calculate inner product, you have to make the first one transposed and multiply by the second one. Our target is to have, if we calculate the instantaneous power in the new frame, okay, by submitting the product of a three, the product instantaneous power product, that's also inner product in the new frame. They are exactly the same. So let's see how we can make those two be equal. So in order to get the result in the new frame, so we assume so the vector of voltage in the old frame is equal to the new frame applied by an inverse transformation, right? So this will be same. It's equal. The next one, we get rid of this parentheses. So this one is unchanged, and the left become this the new voltage vector transpose multiplied by this one. This one is actually the inverse of transformation, then is transposed. Okay, so now you see those two are actually exactly what the target, and we just need to make this one to be identity matrix. So if those two, this product is identity matrix, which means if you think about, okay, so this is like an inverse of transformation, right? This is like inverse then transpose. So which means inverse then transpose is actually the P itself. In other words, so this transpose matrix is also the inverse of this matrix. Okay, does that make sense? So this is P. P will be equal to P inverse transpose. So which means the P's transpose is also its inverse. So mathematically speaking, this feature is called orthogonal matrix. So if any square matrix has its transpose be equal to its inverse, this matrix is called orthogonal matrix. So actually, mathematically speaking, there's the theorem saying if you want to make any square matrix as transformation to be power invariant, which can preserve inner product, that matrix had to be orthogonal. So if you don't know this fact, that's fine. We just need to know. So this one has to hold. Okay. So next, you just simply make this one, you calculate this inverse and make that one also be equal to its transpose. So you calculate this inverse and make that one to be in transpose. So there's only one solution of the three case value. Okay, so KD, KQ are both square root of 2/3, and K0 is just a square root of 1/3. All right, so we immediately get the final 0 DQ transformation. Okay, next, well, 1 minute, I just got some
What? Yeah, we'll let you.
Okay. Okay, let's figure out how we can transform this flux linkage equation into the new frame. So this is still our original equation, right? So those L blocks are all state dependent. Oh, actually, only LRR is actually constant. The other three are all state dependent. So we have this part transformation applied to the current vector and the flux linkage vector, and we assume it can transform into a new frame. We change the subscript from ABC to 0 DQ. So which means the first element 0, second D, and third is Q. Because for the rotor element, flux linkage or current, they're already in 0 DQ, right? Like for the current, the first element is F is in D, and capital D is in D, and capital Q is in Q. So they don't need to be transformed. So we just add identity matrix here. So only need transformation to transform the stator winding in the ABC frame. So which means the original flux linkage vector is equal to the new flux linkage vector after applied by this transformation. So the P inverse is here, is just to transform the ABC to 0 DQ, but for P inverse, it just transfer from 0 DQ back to ABC. So next, we just need to plug in those two equations into the original flux linkage equation to replace the original flux linkage vector by the transform vector. Then we make some simplification. So this is what we have. So this is the transformed flux linkage vector. This is transformed current vector. And this is whole bound become our new indulgence matrix. So you see so the P will be applied to this one, and P minus will be applied to that one, And finally, the IRR doesn't need to be transformed at all, because that's already in the new frame. So let's see what happened. We just simply define this one as L prime. I don't go through the detailed step, but it's very, very easy to prove. After transformation, everything becomes theta independent. This is the new indulgence matrix. So let me quickly explain what each element means. So this L0 means zero sequence indulgence. So that's only the indulgence in the neutral line. Zero here is just the zero current, which is the sum of the average of the three-phase current. LD is actually the total self-indulgence in the D axis for stator winding. So original matrix, if we go back to here. So when we talk about self-indulgence, we for stator winding, we mean LA, LBB, and LCC. After the transformation, this only become but ABC is actually in the original frame, but you can assume those LA, LBB, and LCC have two components. One is in the D, the other is in Q. After transformation, in the D axis, they become just this single indulgence, and then Q will become LQ. So those self-indulgences between for AA, BB, and CC now become just two components. This KMF, so this KMF is actually linking this flux linkage in the D axis, to the F current. So you know, actually, this is like a mutual indulgence coupling the D axis and the field winding. So the flux linkage is in the D axis, and the current is field winding. So it's actually this is a mutual indulgence between the stator winding in D axis and also the field winding in D axis. This is actually the coupling the flux linkage in stator flux linkage in D axis and the damper current, the current in the damper winding D axis. Okay. And this one is actually coupled the flux linkage of stator winding in Q axis and the damper winding in Q axis. So finally, this block doesn't change. That's exactly the same as the original because they don't need to be transformed. So there's, if you keep everything in the original, those matrices, so those MS, LM, so those constants will stay. But for this representation, we make it simpler. By defining those one, just make the matrix be simpler. And finally, K is actually equal to the square root of 3/2. For 422 students, you don't need to know how to prove this one, but I will give a 522 student homework to prove this equation. So it's not very hard. It just takes do some labor. After labor work, you will be able to get this equation. Another way to rewrite this equation is we rearrange all the elements. So originally we have this one is from the stator and this one from rotor. Because right now we have three axes, 0, D, and Q. We can make the first row to be 0, the next 3 to be D, and the last 2 to be Q. So in the D axis, we have 3 equations, one from stator and the other from a rotor. For Q axis, we have one from stator and one from rotor. So if you write this in this way, the indulgence matrix become diagonal because we have one element, we have another 3x3 block, and we have this 2x2 block. We have diagonal block matrix. So that make the equation simpler. The process of this slide and the past slides about proving this equation, there will be some sections on both the Sadek's book and Quinter's book. My slides basically follow the naming notation conventions from Sadek's book. If you read Quinter's book, the Quinter book use another system of notation. I gave you this table, just help you to understand what that book is talking about. Okay. Okay, we still need to work on that voltage equation. So we have this voltage equation. This is column of voltage element, and this is the resistance and the current, and this is first order derivative of flux linkage. We still need to transform this equation into the new frame. So now we apply the transformation to voltage, current, and flux linkage. So similarly, we don't need to transform anything on the rotor because those already in the new frame. So you will see I in the transformation. So we just plug in those three into this equation. We'll have to this step. We get to this step. This is a transformed voltage vector. And this one will be the transformed resistance vector. And for the last item, to transform the flux linkage vector, especially its first order derivative, we first replace the flux linkage vector by the inverse transformation applied to the transformed vector. And outside we have another transformation. So we need to simplify this one. So one thing we need to pay attention is actually P is not constant. So if we calculate the first order derivative of either P or P inverse, we cannot treat this one as constant. You cannot just apply this first order derivative directly inside only to this flux linkage. So you have to use this formula, use the product rule. So if you calculate first order derivative of a product A and B, so what do you get? You get first A multiplied by the B prime, right? Then plus A prime multiplied by B. So when A and B are both time dependent. So here, both P and psi are time dependent. Because P is theta dependent, theta depend on time. The next step, we need to do this one. Okay, so we'll have, we need to calculate first order derivative of this one multiplied by that one. And first step, we apply the derivative to the second one, and there will be another, right, P inverse outside, then multiplied by P due to this one. So this one will be canceled. So this is one item. And the second item is actually we treat this P inverse, we treat this one as inverse, as constant. So the first order derivative will be applied to the P inverse. So next will be figure out what this one is. And to calculate this one, we know theta P inverse is actually theta dependent. So we can first calculate the derivative with respect to theta. We calculate this one, then multiply by derivative of theta with respect to time. So d theta dt will be omega r. Okay, and this one we just go ahead to calculate the first order derivative. You just plug in the P inverse. This is the first order derivative of a P inverse with respect to theta. And this is P. You do some simplification. I basically gave you one matrix, 3x3 matrix, and only two non-zero elements. This step I have to show the process because this is very important. This is actually the dominating factor determining how the voltage is generated. We'll show this one in the later equivalent circuit. So if you ignore this one, the generator is not able to generate electricity. Okay, so the original atom in that equation will basically just this vector with 1 0 in the zero sequence, another 2 in the D and Q axis. Okay, because from the flux linkage equation we know the psi Q and the psi D, so we can get these detailed formulas for this item. Finally, for the transformed resistance matrix, this is very simple. If we treat all winding have the exactly same resistance. So this one can be simplified as just the resistance of winding A multiplied by the identity matrix. All right, so now we're ready to have our next equivalent circuits in the transformed, using the transformed equation in the new frame. To summarize what we get for the voltage equation, so we have it's still 6 equation, right? We have in the 0 reference, D reference, and in the Q axis. The resistance matrix is still diagonal. For the 0 sequence, we assume that's same as, because that's from stator, that will be same as resistance in the stator winding. And the D will also RA, and the Q is RA. And the other, the field winding will still have the field winding resistance, and damper winding will have their original damper winding resistance. So the inductance matrix that become diagonal block matrix will have a 0 sequence, and this is the D axis, 3x3 inductance matrix, and 2x2 for Q axis, and most of other elements will be 0. And at the end, we have 2 additional items that comes from the derivative of P, time derivative of P. Okay. And if we draw the new circuit and we add a 0 sequence, so there will be, if we assume that the 0 sequence, the neutral wire may have some current under some unbalanced condition or fault condition, so we need to put inductance and the resistance here. So where do those items go? So they will go to the first element. So if a balanced condition, you don't need to add those two, you can ignore. But for unbalanced condition, you want to use this equation to do any calculation, you need to add the neutral resistance and inductance by 3 times to the first element. Okay, let's go ahead to draw the new equivalent circuit. This is the new equivalent circuit. On the rotor side, that's same, right? Doesn't change. But on the stator side, we have 3 new circuit, and 1 0 and 1 D and 1 Q. And the coupling only happened in each axis, right? This is D. So the coupling is only happened between the stator D axis winding and the field winding and the D axis damper winding. And this coupling is only between the Q axis stator winding and QS damper winding. So we don't need to consider the coupling between D and Q. That's completely isolated between the 0, D, and Q. So this gave us a much simpler circuit. Another thing we need to pay attention is we have a source added to each axis of the stator winding. So that is because of the time derivative of P. The P is a transformation, which itself is state dependent. And when you calculate first derivative of P with respect to time, so that will give you some omega, right? Omega here is just basically caused by d theta dt. So that will give us some fictitious source to each of the stator winding. And especially for the new source added to the D axis, that's actually the negative omega r multiplied by psi q. So this one is a voltage caused by Q axis flux in D axis winding. So because of the flux linkage in the Q axis, and also the rotor revolving at omega r, this will result in a voltage added not to Q, but added to D. So similarly, the other one, this omega r multiplied by psi D, which is a voltage caused by D axis flux linkage, but to the Q axis winding. So what are they? If you know this equation based on the original Faraday's law, this equation said any circuit, if you have induced voltage, that must be from the two type of component. One is change of electric field, the other is change of magnetic field. So for the change of magnetic field, that will in the form of the product of some speed multiplied by some flux linkage or magnetic field. So which tell exactly what those two are. Okay, so for generator, if the generator, the speed is 0, so what will happen? Those two will be gone. So electricity going to the grid will be mainly from this field winding, because that's become the only source in the whole circuit. But keep in mind the voltage in the field winding is very low. The purpose is only to generate magnetic field. So actually, but if the generator operates at a very high speed, like 60 hertz or 377 radian per second, so even the flux linkage can be small, but multiplied by the speed can be very high. So basically, those two are mainly the true voltage source of generator. So that actually explains generator is not transformer. A transformer doesn't have this item, right? Transformer is transform whatever change on the primary winding to the secondary winding for the electric field. But generator mainly generate voltage by this speed. Basically, the generator utilizes speed voltage to send electricity. Okay. Yeah. So let's continue on Wednesday.